Hello, everyone. Welcome to another review session. I just got home, so I'm getting everything set up. Give me just a couple minutes here. Today we are going over Unit 1 of AP Chem, which is Atomic Structure and Properties. We will be going through this packet, this PDF of questions that has multiple choice questions and free response. If you want to follow along either on the live or if you want to try them on your own, this packet is available on my Linktree. If you go onto my Linktree, it's under like useful information or helpful information or something, and you can find it there. It's a PDF, completely free. Like I said, I'm just getting home, so I just need to get a couple things set up here. How is everyone Saturday? Is everyone excited for the eclipse? Is anyone going to be in like the path of totality? My place is exactly in the 100% totality. So I'm gonna obviously record some stuff for you all to see if you cannot see the eclipse. Where am I going here? And we go here so we can see myself. Beautiful. What's everyone up to? This review session is going to be on atomic structure and properties, Unit 1 AP Chem. I have a PDF of all of the problems that we're going to be going over today. So that is on my Linktree if you want to follow along. If not, I will just change settings over in just a moment and we'll get started. As with all of these review sessions, we'll go over some stuff for about 10, 15 minutes, like a very brief overview of everything in the unit, and then we'll go right into these practice problems. Let's see, I'm going to have a sip of my coffee. And yeah, what kind of questions do you have? This is on Unit 1, so today's review session is going to be on atomic structure and properties. These review sessions, I now have a YouTube account. So I am taking all of these review sessions. If you have to leave for some reason and you miss something that you want to go over, the live recordings of these review sessions are going to be up on my YouTube. I have the first two of them up there already. The first one is on equilibrium, and the second one was on Unit 6 thermo, so heat capacity, heat, Hess's law, all of those. I was banned from the Kinetics live for some reason, so I'm going to record myself just going through that problem set, and I'll post that onto YouTube as well, so you can see that. But for everyone just joining, we're going to get started in just a minute or two. I just got home, so I'm trying to catch my breath a little bit while I'm just talking. It's real fun. We are going to go over atomic structure and properties today. So this is Unit 1 of AP Chem. And this is going way back to the very beginning of AP Chem, talking about protons, neutrons, electron configurations, going from grams to moles, all of those. This particular one is not going to include intermolecular forces. That is Unit 3. And I'm actually doing Unit 3, I'm doing 2 full sessions on intermolecular forces. That is the most heavily tested unit of the AP test. So that will be, so today is the 6th. Today is Unit 1. Then upcoming Wednesday, the 10th, is Unit 2. And then the following Saturday and Tuesdays will be Unit 3. So that'll be IMFs and solutions and all of those. So we're going through. If you want to follow along with the PDF, this is available on my Linktree. If you just click, it's the first link under helpful information or something, review session materials. You can go ahead. These are pulled from AP class. What was I going to say? These are pulled from AP test practice sessions from College Board and everything. So these are AP AP questions, AP style questions. I just got transported to innovation on my day off. Oh no! Is that Morgan? Hi, Morgan. So yeah, we'll get started. I hope everyone is having a fabulous day. What I'm going to do, it'll look a little shaky for a minute or so. I am going to switch from this setup to my other setup so you can see my iPad. So it's going to be a little shaky. I apologize. Let me turn this on first. Beautiful. And we go like this. And I need to flip the screen. Flip camera. Beautiful. Now, last time when we were doing this, it wanted to keep auto-focusing. So if it starts zooming in and out, in and out, in and out quite often, just let me know and I will try and fix it. So let's go ahead and get started. We'll start talking. Again, this is going to be a very brief overview of atomic structure and everything you need to do in Unit 1. And then we'll go through, we have a bunch of practice problems. We have about 25 or 26 multiple choice and a few free response. The free response for Unit 1 is they don't put a lot of free response on the AP test from Unit 1 because Unit 1 just it's like the bare minimum and everything branches off of it. So you will be tested on Unit 1 concepts in free response, but they'll be in a different manner. They'll probably be focused on like a Unit 3 question or a Unit 3 problem where you have to use something that you found or some knowledge of atomic structure. Help, what is this AP Chem? It is Advanced Placement Chemistry. So I think it's College Board. I don't know if it's just a US thing. I have a feeling that it's just US, but I'm not positive. But let's go ahead and start talking about atomic structure. I'm just going to move over. So when we're talking about atomic structure, we have what's known as like the atom. And inside of an atom, we have protons, we have neutrons, and we have electrons. Those are the three things that we have in our atom. Now, we have protons and neutrons. They exist inside of our nucleus. So if we had it's like the center of our atom. So the center of our atom, we have our protons and neutrons just sort of chilling out in the center. And then we have electrons all around our nucleus. And so we can use this notation to help us figure out the overall atomic structure of an atom, overall structure of an atom. And we can use this. We use the periodic table, the chemical symbols. And so let's take, for instance, calcium. So calcium has an element symbol of Ca. So we have C and A as our element symbol. Then we'll have a number up top and a number on the bottom here. So calcium's numbers are 40 and 20. So we'll do 40 up top and 20 on the bottom there. What do these numbers mean? Well, this 20 is the atomic number. The atomic number we can find using the periodic table. So if we have a periodic table, we look at the periodic table, and it's really the number on the periodic table. So hydrogen is 1, helium is 2, lithium is 3, so on and so forth. Our atomic number tells us the number of protons in our element. So calcium, since its atomic number is 20, calcium has 20 protons, and that will not change. So calcium will always have 20 protons. As soon as we change the number of protons, we change the element. So let's say we have 19, our atomic number, this changes to 19, so we have 19 protons. Well, now we're no longer talking about calcium. We're talking about something completely different, a different element. Well, what is this 40 up here? That 40 is our atomic mass. So we have our atomic number, which tells us the number of protons, And then our atomic mass, that tells us how much our atom weighs or our element weighs. And we can find that by adding up our protons and our neutrons. So this is the total number of protons and neutrons added up together. So if we had an atomic number of 20 and an atomic mass of 40, well, in calcium, we have 20 protons based on that atomic number. And then since we know we have 20 protons and our atomic mass is 40, if we were to do 40 minus 20, that'll give us 20 for our neutrons, because if we were to add up our protons and neutrons, we would get a total number of 40, which is our atomic mass. Now, because there can be another number up top here, so there could be another number up at the very top of this element symbol here. And that number is the charge. Now, when we have a neutral atom, when there's no number up top, like in this particular case right here, our number of protons will equal the number of electrons. So in the case of calcium, without a charge, our number of protons equals the number of electrons. And it just so happens that the one example I did, they all are 20. But that's not always going to be the case. Let's say, in fact, we had a calcium 2+ charge. So instead of this calcium 2040, we had calcium 2040, so 20 on the bottom, 40 on top, and then we had a 2+ charge, I'll say. Does AP Chem's periodic table give this much info? So AP Chem's periodic table will not give you everything that you see here, but if you're asked a question like this, it will give you the atomic number. So actually, let's look here. We have the atomic number, and then it will give you your atomic mass. It will not give you your electrons. That is something that you will have to solve for on the side. So if we took calcium, 40, 20, and a 2+, well, we still have 20 protons because that atomic number will not change. That tells us number of protons. The 40, again, that's the number of neutrons and our protons. So that's still going to be 20 neutrons. But now we have a +2 charge. So in order for us to get a +2 charge, we have to compare the amount of protons and electrons. A proton has a positive charge, an electron has a negative charge. So if we're positive, we have more protons than electrons. And in order for us to get a +2, we need 2 more protons than electrons. So our electron count here is going to be 18 electrons, because when we add up our protons and electrons, we have 20 positive, 18 negative, so that becomes 2 positive overall. So it's not always going to be the case where you have 20, 20, 20, or the same number of each. In fact, you could have a different number of neutrons too. You could have this atomic mass number up here could be, let's say, 50. And if it's 50, then we know that our protons don't change, but our neutrons are going to change. And so we can just take 50 minus our 20 protons, and we would end up with 30 neutrons. How are we doing so far? This is, a very brief overview. We are going to start talking a little bit more complicated. This mass number, so this 40 up here, that is our atomic mass unit, or atomic mass, and has units of AMU, which is atomic mass unit. A lot of people get confused with atomic mass unit because later on, we start talking about grams per mole. These are essentially the same thing. AMU is essentially the same thing as grams per mole. AMU essentially takes the mass of your element, of your atom, and compares it to the mass of one hydrogen. But if we look at a periodic table, the mass of one hydrogen is about 1. So when we really do AMUs, it's the mass number, so like 40, for instance, here, divided by 1, which is 40. Now, grams per mole, that's just letting us know how many grams of our element are in 1 mole. Everyone gets confused by the mole. Everyone I know gets confused by the mole. The mole is simply a way for us to quantify things. Think about like a dozen, right? Dozen isn't a number. It just tells us about a number. It tells us that we have 12 eggs, 12 chickens, 12 breads, 12 computers, whatever it may be. When we have a dozen, we have 12. A mole is something similar. Instead of 12, it is a very large number. So 1 mole equals 6.02 times 10 to the 23rd something. Just like a dozen equals 12 something. That's all a mole is. A mole just tells us a number of something. So when we go and we say, oh, well, we have 5 moles of carbon, what we're really saying is we have 5 times 6.02 times 10 to the 23rd carbon. Very, very complicated number, very large number, but we're working with things on the atomic level. We're working with very, very tiny things. Avogadro's number, yes. So Avogadro's number, we'll talk about in just a moment. So if we were to, let's say we start out with some number of grams, and we want to figure out how many moles of that substance we have. Well, we can go from grams to moles using an element's molar mass. And that comes directly from the periodic table. That's our numbers, our atomic mass number. Yes, always when in doubt, convert to moles. Absolutely, because moles are the epitome of chemistry. When we're going from one thing to the next, whatever it is, if we're going from aluminum to aluminum oxide, if we're going from carbon to nitrous oxide, whatever it is, the only way we can go from one substance to the next, we have to be in moles. So when in doubt, I love that. When in doubt, go to moles. But sometimes we want to go a bit further. We don't care about moles necessarily. We want to be in molecules, or we want to know the amount of atoms, or really anything. We want to go a little bit further. And this is where we use Avogadro's number. And we can go from moles to molecules, or atoms, or any other sort of whatever it might be. And this is where we use Avogadro's or avocado's number. And Avogadro's number is this 6.02 times 10 to the 23rd. That is the placeholder. So what we're really saying is Avogadro's number is 6.02 times 10 to the 23rd something for every mole, for every 1 mole. So this something that we have can be molecules, it can be atoms, it can be chickens. I don't know why I say chickens a lot. It can be paper. You can really find a mole of anything. In chemistry, we use moles to figure out molecules, atoms, bonds, things like that. So these two things, these two conversions are going to be very, very helpful when we do a bunch of calculations. As we go from grams to moles, moles to molecules, we can then go backwards. Like let's say we have a number of atoms, but we want to know how many grams that is. We just follow the trend. We go using Avogadro's number from atoms to moles, and then moles to grams. A lot of teachers teach this as, oh gosh, I don't even know how they teach it. If you have a mass and you want to figure out moles, you have to divide it by the molar mass, and that'll equal moles. I think that's the equation. It equals mass divided by molar mass. This is a good equation, but I like to use dimensional analysis. And the reason I like to use dimensional analysis, and I'm going to do a lot of the problems today with dimensional analysis, is it's because it does it all in one step. You don't have to keep track of everything, and all of your units will cancel out. So let's take a look at what dimensional analysis looks like. If we started with 5 grams of carbon, for instance, and we wanted to get to molecules of carbon. So we want to go from grams to molecules. Well, the first thing, when in doubt, we have to go from grams to moles, and then we're going to go from moles to molecules. We have 2 steps here. So I'm going to write what we're starting with, 5 grams of carbon. Now, I'm not going to worry about numbers yet. I'm just going to look at units. Now, with units, I want to cancel out grams of carbon. I no longer want to be in grams of carbon. And so I'm going to put grams of carbon on the bottom of this unit conversion factor, because when we do the conversion, when we multiply everything out, the grams will cancel out. That's good. And we want to go into moles of carbon. Now, how do we go from grams to moles? Well, we use the molar mass. And molar mass we find using the periodic table. If we look at our carbon, there's going to be a little atomic mass number. And that number is 12.01. Did I get something wrong? I see a question mark, grams per mole. So I'm gonna see if there's an actual question there. But what we want to do is we want to go from grams into moles. So we're canceling out grams and we're going into moles. So this allows us to go, well, in 1 mole, well, let me actually write it like this. We know that the molar mass of carbon is 12.01 grams for every 1 mole. This allows us to take that number with grams and put it with our grams. That's 12.01 grams for every 1 mole. So it's like the inverse here. We're really dividing like we said before, but we're just canceling out those units. So when we cancel out the units, now our grams will cancel out and we'll be left with moles. But we don't want to be in moles. We want to be in molecules. So now we do one more unit conversion. We want to get rid of moles of carbon and we want to go into molecules of carbon. Well, according to our conversion factor, we have to go from moles to molecules. We use Avogadro's number. Now, Avogadro's number, that is the 6.02 times 10 to the 23rd molecules for every 1 mole. And again, our units will cancel out, leaving us just with molecules. So now all you have to do is multiply the top together, multiply the bottoms together, and then divide, or you can plug it right into your calculator as is. I don't have a calculator with me, but what you'll end up getting is some number of molecules of carbon. We went from grams to moles to molecules. And so I love dimensional analysis because we're able to do things like this. Awesome. All right. So we'll go over a couple more things and then we'll jump into some questions. I am going to make a new page just because I thought I could do all of this in 2 pages, but couldn't. Molecules and particles the same? Yes. So typically what you will see is, let's say we have C2H4. When we use Avogadro's number, we have to go into molecules first, and then let's say we wanted to go into atoms of carbon, then we use that stoichiometry. We have 2 carbon atoms in this one molecule. So molecules, particles, things like that, those are going to be the same. Molecules and atoms, they are slightly different. Atom refers to your element, and molecule refers to your overall piece. All right. So I'm going to quickly talk about, what am I going to quickly talk about? Electron configurations. I'm going to quickly talk about electron configurations because that'll be a majority of these. Electron configurations I'm going to do right now. Lewis structures will be to the next session, so Wednesday. I do private tutoring, but I am completely full right now, unfortunately. All right. Let's go ahead and talk about electron configurations. Because a lot of people struggle with these. Now I have, Wednesday it's at 7. I have a pinned video with all of these things. Electron configurations, there's a lot of information, and I have a video on TikTok, I think it's a 9-minute video that actually goes into detail how to do all of the electron configurations. And so we are going to just briefly talk about what an electron configuration is, how we find it, and then we'll go over some problems later on when we do the multiple choice problems. So, electron configurations. Before we talk about that, let's go ahead and just draw out the structure of an atom. So we have the center, which is our protons and neutrons, that's our nucleus, and then around that center, we have these rings of electrons. I'm not an artist, I'm a chemist, so please don't mind my poor circle skills. Now, each one of these, starting from the nucleus and going out, is given a number, and that number is our shell. So we have n equals 1, n equals 2, n equals 3. And you can think of these shells like the rows or periods on the periodic table, where the first shell, that n equals 1, is the first row on the periodic table. And then it kind of goes, n equals 2 is the second period, third is the third, so on and so forth. Each one of these shells of electrons has a certain number of, or each one of these shells has a certain number of electrons in it. So we have n equals 1 has 2, and then we could have, let's say, 1, 2, 3, 4. Let's see if we did something like that, where we have our 4 electrons here. So it really depends on the shell, but each shell has subshells. So let's talk, I'm explaining this poorly. My whole video goes through pretty well, but essentially, this right here is the atomic structure of carbon, and I'll explain why in just a moment. So we have carbon here. Well, the reason I know it's carbon is because we have 1, 2, 3, 4, 5, 6 electrons. And these 6 electrons are around our protons and neutrons. Now, I don't know about you, but I wouldn't want to draw this anytime I'm talking about the electrons of carbon. I'm a chemist, not an artist. As you can tell, my circles aren't there. It takes a lot of room. I don't want to draw this. And this is where we can make shorthand to talk about the electrons and where they are. Because an electron configuration is just a barcode, really, to tell us how many electrons we have. So let's say, I'm going to write the electron configuration for carbon, and then I'll tell you how I figured it out. I would much rather write this. So we have 1s2, 2s2, 2p2. That is the electron configuration for this. These two things, that picture and this little string of letters and numbers, the same exact thing. They tell us the same thing. I'd much rather write this, to be honest. But how did I get this? Well, we use the periodic table. That's the holy grail in chemistry is the periodic table. Now, when we read, typically in the English language, we read left to right, top to bottom. And so what we do is we find these values based on that periodic table. What I'm going to do is I'm going to kind of erase this, and I'll just draw one of these. So we have 1s2. This 1 comes from the row or period on the periodic table. This letter is the subshell, or what we call a subshell. This is also, we can find on the periodic table as the block. And I'll go over what that means in just a moment. And then this is the number of electrons in that subshell. So this looks a little confusing, but if we break it down, we have the row on the periodic table, the block it's in, and the number of electrons. So let's look at the periodic table. We can break the periodic table down into 4 blocks or 4 sections. We'll have the S block, which is the first 2. We'll have the P block, which is the next section over here. The D block is our transition metals, and the F block is the bottom portion. Oh, what happened to my thing? Hold up. Atomic structure, there we go. So when we read these electron diagrams, or when we sort of read the periodic table, all we do is we go top to bottom, left to right. We're always going to start with hydrogen, and then we just go over. So hydrogen, we're in the first row on the periodic table. So I'm going to write up here. We have the first row. We start out in the S block. So we have 1s, and every element we pass gives us another electron in that block. So we have hydrogen is 1. Now helium all the way over here, that is technically considered an S block. So we have 1 and then helium, which is 2. So that brings us 2. Now if we continue reading left to right, we go through the full first row, then we go down to the second row. In the second row, we are now in the second row. We hit the S block first, and then we go over 1, 2 elements. And those 2 elements each bring, it's hard to do this with a piece of paper on top of my iPad. Those elements each bring an electron, so 2s2. Then we continue left to right, go all the way over. Now we're hitting, still on the second row, but now we're no longer in the S block. We are in the P block. So we can go 2p, and if we go over to carbon, we go through boron 1 and carbon 2, so we have 2 electrons for carbon. And that's how I got the 1s2, 2s2, 2p2. Now you do this for all, you can go all the way down the thing. You could do all the way down to like lead or even radon or anything like that. You start at the very top and you go all the way down. Now, these are the basic ones, so very, very basic. When we get down to the d orbital, it is rho minus 1. And then the f orbital is rho minus 2. That's the only distinction. Everything else will be the same. It has to do with energy levels and such. Okay. I know that was a very brief overview of electron configurations. We will go through a bunch of examples of those as we go through our worksheets. So now we're going to start going into some practice problems. If you want, those are the answers. If you want how to tell which subshell is lost first. That's a good question, actually. So if we had, you always go to the valence shell, which is the highest number. So your valence shell will always be your highest number. And then you go to the, so SP, it goes in the order of SPDF. So if you have a subshell 4S, 4D, and 4P, you would lose from the 4D first, just based on things. So you would just look at the numbers out in front. Typically, you'll be asked that with like a 4S and 3D. If it was 4S2, 3D, 9, this would actually be 4S1, 3D, 10. There's some weird electronics here, but we'll go into that and stuff. I have a whole video going over electron configurations. I will pin it after this so you can find it a little bit easier. But for now, what we'll do is we'll go right into some of these problems. If you want to focus or if you want to follow along, you can have this PDF. It is on my link tree. It's all questions from AP exams, past AP exams. But there are also benefits to doing this if you're not in AP Chem. It's good practice. All right. So let's go through number 1. The first one here. We have how many carbon atoms are contained in 2.8 grams of C2H4? Okay. So let's make a plan. We want to figure out how many carbon atoms are contained in 2.8 grams of that. So we're starting with grams of C2H4. Now, the only way to go from grams of something into something else, we have to be in moles. So we'll go from grams, then we'll go into moles, but we will be in moles of C2H4. Then we will go into molecules of C2H4. What happened to my pen? There we go. And then we'll go into atoms. So this is similar to one that someone was asking beforehand. How can we go for are molecules and atoms the same? They are different. So let's start out. Well, we're given 2.8 grams. So we'll do 2.8 grams of C2H4. Now we want to go from grams to moles. Now doing dimensional analysis, I want to cancel out grams. So that's going to go on the bottom, grams of C2H4. And on top, I'm going into moles of C2H4. How do we go from grams to moles? Well, we use the molar mass. In 1 mole of C2H4, there are 28.06 grams. But how did I get that 28.06? Well, I looked on the periodic table. Over on the side here, we have carbon. If we looked on for the atomic mass of carbon, that would be 12.01. But we have 2 of them, so we have to multiply that by 2. And then for hydrogen, if we looked at the atomic mass, that's 1.01, but we have 4 of them. So 12.01 times 2 gives us 24.02. And then 1.01 times 4 gives us 4.04. And when we add those up, we get 28.06. So when we add up when we find molar masses of whole things, we just add up the amount of atoms that we have in our compound. So we have this now. We're in moles, but we don't want to be in moles. We want to go into molecules. So I want to cancel out that mole of C2H4. And we want to go into molecules. I'm going to put this up top, C2H4. Now, how do we go from molecules into moles? Well, we use Avogadro's number. Avogadro's number is just a placeholder, and that says 6.02 times 10 to the 24 something, whatever that is. So this one's molecules, are in 1 mole. But again, we're not talking about molecules here. We're talking about atoms of carbon. So again, one more time, we have to do another unit conversion. We are now in molecules of C2H4. We don't want to be in molecules of C2H4 anymore. Molecules of C2H4. We want to be in atoms of carbon. So if I were to give you 23rd, that is a 3. It's just a little funky. I'm sorry if I said 24th. I may have said 24th. 23rd. There we go. How many atoms do we have in one molecule? Well, if we look at one molecule of C2H4, we see 2 atoms in there, the 2 atoms. And when we do this math out, the units, the grams will cancel, moles will cancel out, molecules cancel out, and we're left with atoms of carbon, which is exactly what we wanted. And so we end up getting, if we do the math out, 1.2 times 10 to the 23rd atoms of carbon, which is choice A. A lot of teachers will not teach dimensional analysis like this. They will teach you, okay, you have to go from grams to moles, you divide by the molar mass, you'll get an answer. Then you want to go from moles to molecules, you multiply by Avogadro's number, and then you'll get an answer. And then you'll have to figure out atoms from there. You'll have to do another thing. And so I don't like that because you have to do different steps. I like to do everything all in one giant step rather than piecewise. You can do it stepwise. If you wanted to divide by molar mass, that's totally okay. And then go on and multiply by Avogadro's number, absolutely okay. All right, let's go ahead and do number 2. A solution is prepared by adding 16 grams of CH3OH with a molar mass of 32 grams to 90 grams of water with a molar mass of 18. The mole fraction of CH3OH in this solution is closest to which of the following? So now we're talking about mole fraction, which is this funky little chi symbol here. And that chi symbol tells us mole fraction. And we can think of mole fraction as part over the whole, or number of moles of whatever we're looking for, in this case CH3OH, divided by the total number of moles in our system, CH3OH plus our moles of water, because we have those 2 things in our solution. So if we start with moles of this divided by the total amount of moles, we will get a mole fraction. And that's all a mole fraction is part over whole. What we need to figure out, though, are each of these pieces. We're not given any sort of moles here, but we can figure that out. We're given 16 grams of CH3OH, and we want to figure out the number of moles. Well, we use the molar mass in 1 mole of our, and I'm going to put star here just so I don't have to keep writing that. We have, we're told that we have 32 grams of star. So our number of moles of our CH3OH is 0.5 moles when we do that out. Then we have to figure out our moles of water. We have 90 grams of H2O. We want to figure out the moles of water. Well, in 1 mole of water, we end up with 18 grams of water. And doing that math out, we end up getting a total of 5 moles of water. So now all we do is we plug in mole fraction, that is our moles of our part, which we have 0.5 moles, over the moles of our sum, so 0.5 moles plus 5 moles. And doing this out, we end up getting a value of 0.09, and that's close. It's asking us which one is closest to. So this is close enough to A, 0.1. Taking a break from practicing my chem research prez, and I see this, I get that. I was in the lab earlier today and while something was going on, I was doing these problems. So I have a little guide and it was like so much chem. All right. So that's mole fraction. Now let's start talking about mass spectrometry. Mass spectrometry is a scary term, but it's not terrible. So the mass spectrum of a sample of a pure element is shown below. So we have a pure element and we're given this graph here, and we'll go over what that graph means. Based on the data, the peak at 26 AMU, so we're looking at this peak right here, represents an isotope of which of the following elements. So let's talk about what mass spec is. Mass spec is a type of instrumentation that we use to figure out what a solution is, what's in a solution. I actually use mass spec quite often to help with proteins, to figure out what type of protein are in my solution. So mass spec, you put your sample in and it spits out a graph like this. Well, what does this graph mean? Well, this graph is telling us that our mass of our sample is primarily 24 AMU. So our mass of our sample, of our element, is primarily 24. But then we have these other little peaks here, and these are called isotopes. An isotope is, if we look at the word iso equals same. So we're looking at the same element, but something different. Well, if we look, what happened as we went from 24 to 25? We added 1 AMU. And when we add 1 AMU, we are going to be adding 1 neutron. And that's what an isotope is. An isotope is something, it's the same element, just with a different number of neutrons. And so here, we're going from 24, 25 to 26. And we're looking at what this peak is for 26. Well, we want to figure out, first of all, what element we're talking about. And second of all, we're going to be looking at the number of neutrons in that element. But since we jumped 2 AMUs, we're going to do neutrons plus 2 neutrons. Because that's an isotope, right? An isotope is whatever you have plus or minus neutrons. And since we're going 24, 25, 26, we're adding 2 neutrons. So here we're given an atomic mass primarily of around 24. So if you looked on the periodic table, you would want to find an element that is similar in mass to that 24. And the closest one I can see based on what we're given is magnesium. That has a mass of 24.305. So we're talking about magnesium here. Now magnesium has 12 Magnesium's atomic number is 12 and its mass is 24. So this is the number of protons, this is the number of protons plus neutrons. So magnesium alone has 12 neutrons. But we are looking at the 26 peak, meaning we gained 2 more neutrons. And when we gain 2 more neutrons here, we get 14 neutrons. So this mass spec is of the element magnesium with 2 neutrons. Its isotopes are 1 neutron and 2 neutrons. So that peak at 26 is magnesium with 14 neutrons. How is everyone doing? Mole conversions. We will definitely go over some mole conversions probably in the next question or two. Absolutely. So here, for anyone who's just joining, this PDF that we're going over is available on my link tree. If you just go to my link tree under helpful information, you can get a PDF of this if you want to follow along, or you can use it to practice. All of these recordings will be on YouTube. I'm doing AP Chem Review, but anyone who's taking general chemistry or high school chemistry, it's definitely useful. So let's go ahead. And we're going to go on to number 4. The mass spectrum, so we're looking at another mass spec here, of element X, we don't know what element this is, presented in the diagram opposite. So we're given another mass spec here. We have some value here, and then we have its isotopes, right? Based on the spectrum, which of the following can be concluded about element X? So first thing you notice when looking at a mass spec is you want to find the most abundant or the tallest peak. So this is the most abundant peak. And that happens at 90 AMU. So our mass is going to be close to the mass of this element is going to be close to 90. It's not going to be exactly 90 because we have these other isotopes, and those are going to factor into the overall mass. But the mass of our element is going to be around 90. So let's see. Let's go through these answers. X is a transition metal, and each peak represents an oxidation state of the metal. Well, this a mass spec does not tell us anything about oxidation states. It tells us stuff about isotopes. And so we can cross that one out. X contains 5 electron sublevels. This mass spec isn't the graph that we use for that. That's going to come later on when we're talking about photoelectron spectroscopy. So that one's gone. The atomic mass of X is 90. So we said that that's the most abundant peak, but that doesn't necessarily mean that that's going to be the atomic mass, because the atomic mass is the average mass over all of your isotopes. So that's actually not going to be the answer because we have more isotopes that are going to contribute to our mass. And then the atomic mass of X is between 90 and 92. Well, if we look here, a majority of our sample of this element has a mass between 90 and 92. So that is going to be our answer. Remember, mass spec just tells us the relative abundance of our masses of the elements or our compounds. I always forget to have a little, like a cup of water. Instead, I have coffee just off to the side. But I hope everyone is having a fabulous day. Let's go on to number 5. We're going to start talking about empirical formulas now. Something really, really cool. So, a 23-gram sample of a compound contains 12 grams of carbon, 3 grams of hydrogen, and 8 grams of oxygen. Which of the following is the empirical formula of the compound? So now we're talking about empirical formula. So molecular formula tells us everything that's in the molecule. So if we had C6H12O6, that is a molecular formula because it tells us the total amount of our elements in our sample. The total amount, we have 6 carbons, 12 hydrogens, and 6 oxygens. An empirical formula just tells us the simplest ratio. It is the simplest form. Yes. So if we were to divide our number here by 6, for instance, we would have 1 carbon, 2 hydrogens, and 1 oxygen. And this would be our empirical formula. It's telling us that for every 1 carbon, we'll have 2 hydrogens and 1 oxygen. It's just a ratio. So this ratio here is our empirical formula. This is our molecular formula. It tells us everything that's in our sample. So in a question like this, which of the following is the empirical formula of the compound, and we're given masses, what we need to do is go from grams to moles of each one of these and then compare moles, because that's the only way that we can figure that out. What is the benefit of representing a molecule in empirical form and not the molecular form? When you get into upper level chemistry, it helps when figuring out overall ratios. Like if you're trying to do a reaction and you just want to figure out the overall like carbon to hydrogen ratio or something like that. The other thing is it's hard to figure out the actual molecular formula of something in the lab. So using empirical formula is a little bit easier to do. Benefits other than that, I can't think of any right now, but yes. We are going to go over some lab technique questions. Absolutely. So at 23 grams, oh, I already read that. So now what we're going to do is we're going to take each one of these, carbon, hydrogen, and oxygen, and we will solve for the number of moles. So what we're going to do, if we have carbon, hydrogen, and oxygen, for carbon, we were given 12 grams. For hydrogen, we were given 3 grams, and oxygen, we were given 8 grams. So what we're going to do is convert all of those into moles. So we go 12 grams. To go from grams to moles, we use the molar mass of carbon. In 1 mole of carbon, there are 12.01 grams of carbon. And that gives us a value of about 1 mole of carbon. We'll do the same thing for hydrogen. That gives us 1 mole of hydrogen is 1.01 grams of hydrogen. And that also gives us 3 times 1 over 1, about 3 moles of hydrogen. And then we will go into, do the same thing for oxygen. 8 grams, we have 1 mole of oxygen is to 16 grams of oxygen. I'm getting all of these values just from the periodic table, right? They're the atomic mass, they're molar masses. So this gives us 0.5 moles of oxygen. So now that we've solved for all of these values of moles, we're going to take a look at which one is the lowest. We want to look at 1, 3, and 0.5. Whichever one is the least number of moles, we're going to divide all 3 of them by that value. So 0.5 is the lowest, so what we're going to do is divide by 0.5 moles, we'll divide by 0.5 moles, and divide by 0.5 moles. And that gives us 2, 6, and 1. And these values here, these numbers, are the subscripts for our empirical formula. So the empirical formula given here, we have C2, that 2 comes from here, H6, that 6 came from there, and that O1, we don't include that 1, and that 1 goes there. So C2H6O is the ratio of carbons, hydrogens, and oxygens in our compound, which is choice B. I love solving for empirical formulas. I saw a question in there, is this Gen Chem 2 material? It is Gen Chem 1 material. Don't you have to convert to percent first? No, you do not. Not when you do things like this, when we're going for an empirical formula. You just want to solve for moles first and then divide by the least number of moles. All right, we're going to do another empirical formula one. So a compound contains 30% sulfur and 70% fluorine by mass. The empirical formula of the compound is, so now we have something with percentages. But if we look here, 30% and 70%, that equals 100%. So what are we going to do whenever we have a situation like this where we're given mass percentages and they all add up to 100%? Make it moles. We will have to make them into moles, but we have to do something first. Assume 100 grams. Yes, absolutely. I see a couple of you putting that in. So 100-gram sample, because we only have two things in our solution or in our sample, and they both add up to 100%, we can do something called assume 100 grams. So if we assume that we have 100 grams of our sample, that 30% of our sulfur just becomes 30 grams of sulfur, because 30% of 100 grams is 30 grams. And then we'll do the same thing, right? 70% of fluorine, that is going to be 70 grams of fluorine because 70% of 100 is 70 grams. 70% of 100 grams is 70 grams. And then it's the same exact thing that we did, right? Now that we're given grams, we want to solve from grams to moles and then compare the moles. So now that we have 30 grams, I'm going to do a different color down here. We have sulfur. We said 30 grams of sulfur. If we were to figure out the moles of that using the molar mass from the periodic table, 1 mole of sulfur is 32 moles of sulfur, and that's about 0.94 moles. We'll do the same thing for fluorine. Assuming that's 70 grams, we go 1 mole of fluorine. Again, looking at the periodic table, 1 mole of fluorine gives us 19 grams of fluorine, and that is 3.68 moles. We'll compare whichever one is lower. Now that we're in moles, we can do a comparison. Oh my goodness, there is a typo there. Thank you, whoever said that. Let's correct that. 32 grams of sulfur. That's on the periodic table. Yes, I definitely did. Thank you for that. Sometimes I get all chemistryed out and then I get confused with everything. Because if it was moles on the bottom here, for instance, our grams wouldn't cancel out. But we want to cancel those grams out. Perfect. So now that we have this, we're going to divide by the least number, which is the 0.94. So we'll divide by 0.94 moles. We'll divide by 0.94 moles. And that equals 1 and about 4. So if we were to write this, we would S1, F4. And that is our that is our empirical formula. All these moles and everything are getting me confused, which is choice C. So whenever we're given percentages that add up to 100%, we can just go ahead and assume 100 grams. What would be the molecular formula for this question? We would have to be given some additional piece of information. We would have to be told the molar mass of our, I have to slide the puzzle piece. I hate this. If I don't do anything on TikTok Live, they make me do a puzzle piece. You have to be given the molar mass of your molecular formula. And then what you would do is figure out the molar mass of your empirical. Then you would take your molar mass of your molecular, divide it by the molar mass of your empirical. That'll give you some whole number, and that whole number is just what you multiply by. So let's say this was 180 and this ended up being 90. 180 divided by 90 gives you 2, and then it would be S2F8. But you would have to be given some additional piece of information in order to solve for the molecular formula. Great question. All right, let's go ahead on to number 7. After completing an experiment to determine gravimetrically the percentage of water in a hydrate, a student reported a value of 38%. The correct value for the percentage of water in the hydrate is 51%. Which of the following is the most likely explanation for this difference? So here the student found 38% of our solution of our solid was water, but that should have been 51%. So we want to figure out what could have caused us to get a lower percentage than what it should have been. So let's go through. Strong initial heating caused some of the hydrate sample to spatter out of the crucible. So let's think about that. If we have our sample in here in a crucible and we took the weight of it, so this is with water, and then we have another sample here, this is after drying, so no water. If we heated it by a lot and some of this solution spat out of our crucible, the weight of our final without water would be much lower than that. So this would be artificially lower because we lost some from it being spattered out. Now that loss will contribute when we do the calculations. It'll look like we heated that amount from water. So in fact, we'll get a lower mass here. And then if we do a percent or a mass by difference, where we take the initial of this and final of this, we would figure out that that percentage here would be higher. So this actually contributes to a higher percent of water. We want to figure out what caused a lower percent of water. The dehydrated sample absorbed moisture after heating. Well, if we were to heat our sample, get a value here, and then it started to absorb water, now our mass becomes higher over here. And when we do a mass difference, we take initial minus a higher value here. This is going to give us a lower percent. So that could be the answer. Let's go through and just make sure the other answers are correct or are incorrect. The amount of hydrate sample used was too small. This is all due to, when we do gravimetric analysis, this is all due to proportions, right? So if we have a small amount, we're only going to heat up a certain amount of water out of our sample. So this actually has no effect on our amount, because if we heated up a 5-gram sample compared to a 500-gram sample, the percent of water should be the same. The crucible was not heated to a constant mass before use. That also doesn't really play effect in our sample analysis because this is just prior to heating. And then the excess heating caused the dehydrated sample to decompose. That would lead to less mass over on the final, so we would have a greater displacement, giving us a higher percentage. And that is not what we want, so the only correct answer here is B. I know these types of questions with the experiment can get a little confusing. We have to understand sort of what the question is looking for and the experiment setup. So gravimetric analysis is a very useful technique. Let's go on to number 8. We are about halfway done with we're about a third of the way done actually with the multiple choice. And then we have a couple of free response. So I'm expecting to be on for another hour or so. So if you have questions in the meantime, this is a review for AP Chemistry Unit 1. This is Atomic Structure and Properties. This PDF that we're going over with all of these questions is available on my link tree. And then the recording will be available on YouTube. I think it's available the next day on TikTok, and then I'll post it on YouTube after that. So what is the empirical formula of an oxide of chromium that is 48% oxygen by mass? So this is, again, looking for empirical formula. And we're given chromium, and then oxide of chromium means that we only have oxygen and chromium. So those are the only two things in our sample. We're told that we have 48% oxygen. So if we had 100%, not 10%, 100% of our sample, that's the total, minus the 48% of our oxygen, that's going to equal 52% chromium. So here we have 48% oxygen, 52% chromium. Just like the previous one, those percentages are going to become grams. We have 48 grams of oxygen and 52 grams of chromium. Why can we do this? Well, if we assume we have 100%, or if we have 100% total, then we can assume we have 100 grams, And 48% of 100 grams is 48 grams. 52% of 100 grams is 52 grams. So then we'll go through and let me denote this. We have oxygen and we have chromium. So when we go through, we start out with 48 grams of oxygen. We don't want to be in grams. Whenever we do these empirical formulas, we are going to be solving for moles first. I see a lot of people are guessing C, so let's see if we're correct. So we have 48 grams of oxygen. We have 1 mole of oxygen on top using the molar mass of 16 grams of oxygen. That gives us a value of 3 moles of oxygen. And chromium, we have 52 grams of chromium. Converting that into moles using the molar mass, 1 mole of chromium is to 52 grams of chromium, giving us 1 mole of chromium. This one looks a bit easy, but we'll do this out just so we can have practice. We're going to look at the lowest number of moles, and we'll divide both of them by the lowest amount, which is 1 mole and 1 mole, giving us a value of 3 and 1. So we have CrO3, which is choice C. Nice job, everyone. Nice job. I saw a lot of C's in there, so props to y'all. Okay, let's go ahead and do another one of these experimental design problems. To determine the percentage of water in hydrated salt, a student heated a 1.2346, that's a lot of numbers, gram sample of the salt for 30 minutes. When cooled to room temperature, the sample weighed 1.1857 grams. After the sample was heated for an additional 10 minutes, and again cooled to room temperature, the sample weighed 1.1632 grams. Which of the following should the student do next? So, let's sort of map this out. We have that's not what I wanted. There we go. We have a sample, and that sample initially weighs 1.2346 grams. Then we heated it, and after cooling and weighing, it weighed 1.1857 grams. And then heated again. And after that, it was 1.1632 grams. And we want to figure out what to do next. Well, we're looking for the percentage of water of a hydrated salt. This is a gravimetric analysis question where we're heating up a sample to just remove the water, and then we can do a mass by difference. When we're doing gravimetric analysis, we want to heat the sample, let it cool, then weigh it, and then do that over and over and over again until our mass of the sample remains unchanged. We want to look to see when the mass remains unchanged, because let's say this kept going and this is 1.633, 1.1632. That means no more water is coming out of here every time we heat it. But here, we heated it once and it changed. We heated it again and it changed. So we're not at that unchanged point yet. So now we want to reheat the sample until we get this sort of unchanged pattern. And so let's look through and see if any of those match. We have use the smallest mass value to calculate the percentage of water in the hydrated salt. No, we're not going to do that. Repeat the experiment with a new sample and average the results. Well, if we did a new sample and average the results, again, we're not remaining unchanged yet. So that would be good if we remained unchanged, but nope, can't do that. Repeat the experiment with a new sample that has a different mass. Nope, because remember, different masses will have the same percentage of water. Reheat the sample until its mass is constant. That's what we're talking about here, right? So we're going to reheat that mass, reheat the sample until its mass is constant, or use the average of the mass values obtained after 2 heatings to calculate the percentage of water. So that would be okay if we remained unchanged. That keeps popping up. But let's say, for instance, instead of doing it again, and let's say we heated it again, and it was 1.1456, something like that. Well, if we were to just average these two masses of loss, we would be forgetting about the mass lost over here. And so this, we want to make sure that we're taking into account. So we're going to reheat until we get a nice constant mass of our sample. All right. We're going. We got this. So this one, the table is a little small, so I'm going to zoom in and stuff. But number 10. A sample of carbonate rock is a mixture of calcium carbonate and magnesium carbonate. The rock is analyzed in a laboratory, and the results are recorded in the table above. So let's just sort of zoom in so we can see what this table is telling us. We have the total mass of the sample, then we have mass of mass of carbon, mass of magnesium, mass of calcium, molar mass of carbon, molar mass of magnesium, and molar mass of calcium. So we have the overall mass, the mass of each element, and then we have the molar mass of each. That's what that table shows us. Which columns in the table provide all the information necessary to determine the mole ratio of calcium to magnesium in the rock? So what do we need to solve for a mole ratio? Well, first we need the number of moles of our, was it calcium first? So we need moles of calcium and we need moles of magnesium. But in order to solve for moles, we're not given moles up top. We're given values in grams, and then we're given values in grams per mole. So here, we want to take our grams of our calcium and our grams of our magnesium. Those are the values that we're going to want, as well as the molar masses, because we can go from grams to moles using molar mass. So we want grams of calcium and magnesium, and we want grams per mole. I'm going to do this, grams per mole, and that'll give us our moles so we can do a mole ratio. So looking at this, our mass of magnesium is column 3, mass of calcium, there we go, is column 4, and then molar mass of magnesium and molar mass of calcium are 6 and 7. So the answer here, it's a little hard to see with this table and everything, but the answer here is choice C. I saw a question, what app am I using? I am using Notability. That is the app, that is the only app that I have ever used. I know people use like GoodNotes and stuff, but I just bought Notability and that's what I've been using. Whew. All right, we're gonna go and get into some electron configurations now, it looks like. So these will be fun. Taking a moment just to catch my breath. It's a lot of talking on my part. Everyone who's here right now, if you want to, while I take a sip of my coffee, what's your favorite element? Mine is potassium because it burns bright purple. It's a very beautiful purple color. It's like, I don't know, I wish I had a picture of it. It's really very thing. Aluminum, sodium, gallium. Ooh, very nice. Chlorine, awesome. All right, while those keep coming in, I am going to move on. Strontium, very cool. Strontium we use in our solubility rules. In any case, which of the following, let's go on to number 11. Which of the following is the ground state electron configuration of the F- ion? So here, if we were to just figure out the electron configuration of fluorine, that's where I would think would be the best place to start. So we're going to use, we'll talk about ground state versus excited state in just a moment. So we'll use our periodic table, and we're going to figure out the electron configuration for fluorine. So starting at the very top, we'll just work our way all the way until we get to fluorine. So we want to go over to here, but we always have to start at the very, very top. So we go, starting at the top, we're in the first, how am I going to do this? I'll do this. Fluorine, starting at the very top, we are in the first row, so that's 1, and we're in the S block. So that's 1s, and we go over 1, 2. We've used both of those electrons, so we're in 1s2. Then we finish the first row, we're going to hop down to the second row. The second row, we have, we hit the second row. We go over 1, or we're in the S block. Whoa, what happened to my screen? 2s, and we hopped over 2 electrons, so 2s2. I'm going to take that away just for a moment. Let my screen go. Then we're still in the second row. We're going all the way over, and now we go second row. We're in the P block, so 2p, and we go 1, 2, 3, 4, 5. So we're in 2p5. So we have 1s2, 2s2, 2p5. This is our ground state electron configuration of just fluorine, but we want the fluorine minus ion, meaning we're gaining 1 more electron. We're going to act like neon. We're going to hop 1 more over. And so our F minus ion, minus 1, is 1s2, 2s2, 2p6, because we're gaining that 1 electron. How did I get the 2? Which 2? If we're talking about this 2 here, that 2 comes from the second row on the periodic table. So we go first row, second row, so this would be 1s, 2s, 3s, 4s, 5s, 6s, all of that. If you're talking about these 2's up top, the superscripts, those are how many elements or how many electrons you sort of hopped over or passed through to get your, that sort of filled that orbital. So an s orbital, the maximum number of electrons it can contain is 2, and in an s block, the maximum number of atoms in a row are 2. So you just go like 1, 2, and that'll be completely filled. For the p orbital, we were in the second row still, so 1, 2, and we drove all the way over until we got to the p orbital. Now, when we're talking about, so this is ground state, so this answer is choice C here. But when we're talking about an excited state, we'll go over an excited state in a little bit, but I'll quickly talk about it here. Let's say we had, I'm going to do it down here, fluorine, and we had 1s2, 2s2, 2p5. Now, an excited state, that means that one of these electrons that are in the sort of core elements or something is going to be excited to something else. So an excited state could be something like 1s2, 2s1 now, if we take one of those electrons and move it to the new orbital, the higher orbital. So this would be a ground state fluorine atom. This would be an excited state. And the way to tell is, as you're going from left to right, make sure all of your orbitals are filled before moving on. If they aren't all filled before moving on, you have an excited state electron. So like here, the s orbital maximum 2, s orbital maximum 2, p orbital, that's our end. It's not completely filled, but that's our end, which is okay. Whereas underneath it, 1s2, s orbital is completely filled. 2s1, that's not completely filled. Did we end? No, we kept going, and which means that we have an excited electron somewhere in that p orbital. All right, so that is a little bit about excited versus ground state. Let's go on to number 12, and number 12 is asking us to figure out the ground state electron configuration for an atom of selenium. So we'll do the same exact process, right? Going from top left over. We read a book left to right and top to bottom, at least in the English language, right? So we always start up with hydrogen, and we're just going to work our way across going down. So selenium is all the way over here. So we need to go from hydrogen all the way down to selenium. Now, I am going to kind of go a little bit faster on this one. So we have, starting at hydrogen, we're in row 1. We hit the S block and we go over 2. Then we go down. We're no longer in row 1. We're in row 2. We're still in the S block with lithium. And we go lithium, beryllium, that's 2. It's completely filled. Then we hop over to our p orbital, still in the second row, 2p. And we go 1, 2, 3, 4, 5, 6. We're completely filling that orbital. So that's 2p6. Hop all the way down. We do third row. We're in the S block. And that's completely filled. We go all the way through. Move all the way across, still reading left to right. We're in the third row still. Hit the P block. So we go 3p. 1, 2, 3, 4, 5, 6, completely filled. We still haven't gotten to selenium yet, right? We're just hitting argon. We're just hitting argon. We need to get to selenium. So then we go all the way down. We're in the fourth row. So now we're in 4s. We go 4s2. But now we're hitting the D block. And the D block gets a little funky, because the D block, due to energy levels and everything like that, the D block, it's a row -1. So even though we're in the fourth row, we're going to do 3D. So 3D is next, and we completely fill that. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're completely filling that orbital, 3D10. And then we go all the way over. We're hitting the P block again, which means we go back to the row. Row number is 4. So 4p, 1, 2, 3, 4. And then we hit selenium. So this would be 4p4 here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. That is the electron configuration of the ground state for an atom of selenium, which is choice C. Whew, that was a lot. Now, what you can do is, ground state just means that everything is filled before you move on to the next level. If, let's say, we had 3D9, 4P5 or something, that means that it's not completely filled, and that would be an excited state. But I don't know about you, but this is a lot to write. This is a lot to write. We have a shorthand called the noble gas shorthand. And the noble gas shorthand means we take a look at selenium, where it is, and we go backwards until we get to the last noble gas that it passed. And the last noble gas that it passed is argon. So we're going to put argon, or I'm going to draw it down here. We're going to do argon, and we'll put it in brackets. And this bracketed argon is telling us that all of this is in there. So we no longer have to write this 1s2, 2s2, 2p6 as long as we do the bracketed argon, and then we just copy everything down from there, or we continue from argon. So this would be argon 4s2, 3d10, 4p4. That is much simpler to write. However, it's not one of the answers here. So we do have to understand how we get this. But if this is a free response question, you can absolutely do shorthand noble gas shorthand notation. Absolutely. All right. I'm loving this chapter. I don't know about you. I know some of it's a little challenging, but I am absolutely loving this chapter. All right, let's move on. Balancing chemical equations. I do have a video in my AP/Gen Chem playlist going over balancing chemical equations. Unfortunately, I'm not going to be able to get to that unit for a review like this. So this is chemistry. This is AP. This is tailored towards AP Chemistry Unit 1 right now on atomic structure and properties. But anyone taking chemistry, like general chemistry, high school chemistry, it's a very good review. So let's go on to number 13. How many protons, neutrons, and electrons are in this iron atom? So we sort of talked about this atom or this sort of notation before, where we have our element symbol. We have a number up top and a number on the bottom. Now, the number on the bottom, that is our atomic number. That will not change as long as our element stays the same. So as long as the element is not changing, our atomic number will not change. And the atomic number equals the number of protons. So looking at this iron atom has 26 protons. So looking at our answers, we can quickly cross off C, D, and E because they have 30, 56, and 56. That atomic number is the number of protons. What about this 56 number? Well, this 56 number, that is our atomic mass. And our atomic mass is our protons plus our neutrons. So 56 here is going to equal the number of our protons, which is 26, plus the number of neutrons. So we can solve for number of neutrons just by subtracting 26 from 56, giving us an n value that is equal to 30. And that 30 tells us the number of neutrons. Looking at A and B, the only choice left that has 30 for our neutrons is choice A. And then let's quickly talk about why we have 26 electrons. And that's because we don't have a number up here. If we had, let's say, a 2- charge there or something, then we would have a different number of protons and electrons. But then the number of protons and electrons would be different. They wouldn't be identical. But in a neutral atom with no charge, our protons and electrons are equal. So our answer here is choice A. All right, number 14. This is where we're going to get into an excited state question. Of the following electron configurations of neutral atoms, which represents an atom in the excited state? So excited state, that means that we're going to look for so I'm going to write this here. Look for the one that is not filled completely before moving on. And what does that mean? Well, if we look at choice A, well, choice A says, well, 1s2, an s orbital can only have a maximum of 2 electrons. Then we have 2, so that's completely filled, so we can move on. 2s2, again, that's completely filled, and then we move on. Now, our p orbital has a maximum of 6 electrons, but that's at the end, so we can keep that at the end and that's not, what am I saying? That's filled, that's not filled, but it's at the end, so we don't care. Let's look at D. S orbital is filled with 2, S orbital filled with 2, P orbital filled with 6, S orbital filled with 2, P orbital not filled, but that's at the end, so we can't say that it is. Let me talk about this for a moment. So an s orbital, the maximum electron count it can have is 2. P orbital, the maximum is 6. D orbital, the maximum is 10. And then an F orbital, the maximum is 14. So depending on what's already there or not. So let's go over to E. We have S is filled with 2, S is filled with 2, P is filled with 6, S is filled with 2, P is not filled, but that's at the end, so it's not in an excited state. C, S filled with 2, S filled with 2, P filled with 6, S not filled with only 1, but that is at the end, so it's not at an excited state. B is S filled with 2, S filled with 2. P is not completely filled, and it is not at the end, right? We have something coming out after that. So one of these electrons that was a 6 moved up and got excited and moved into the S orbital. So the choice here for the excited state is choice B. So if it's at the end, it can't be excited. That's why if it's at the end, it doesn't really get excited because there's nowhere for it to go. Whereas if it's somewhere in the middle, it can get excited, and then we have something else over that. Hybridization will come on Wednesday when we go over Unit 2. Beautiful. I go live. I have a schedule on my, as a pinned video of when I go live, and I have all of these PDFs sort of available so you can try them either before the live or if you want extra practice or stuff like that. The next video or the next live, typically it's Tuesday and Saturdays I go live, but with the eclipse on Monday and me traveling and everything, yes, I am doing every unit. I've already gone through equilibrium, kinetics, and unit 6 thermo, so heat capacity and heat. And then this is unit 1 atomic structure. Those are all available on YouTube. Well, not the kinetics one. I was banned on the kinetics one, so I'm going to record myself doing the problems, and I'll post those, but I haven't had time to do that yet. But in the meantime, let's go on. The next, I don't think there's any calculations needed in the next like 10 problems. So the next 10 problems are going to be sort of conceptual problems. Yes, it's for AP Chem, but anyone who's taken like general chemistry or chemistry can definitely benefit from this review. So which of the following represents a pair of isotopes? Yes, I was banned for doing kinetics before I go on to this question. I guess on TikTok, there's a lot of trolls recently. And so I was about 20 minutes into the thing, and then I got banned for misinformation. And I appealed it, and TikTok was like, nope, you're banned. So I actually lost live access for like a day or two, which was fun. But in any case, which of the following represents a pair of isotopes? Now remember, an isotope is something with the same atomic number, but different mass number. And that's because an isotope is the same element, so magnesium and magnesium. So same element here would be 12 and 12, but then we have a different mass number. We could have like 24 and 26. And though that difference is just a difference of neutrons. Neutrons don't have a charge, so they don't affect the overall charge, but they do have a weight, which changes the overall mass. So here we're looking for an answer with the same atomic number in atom 1 and atom 2, but different mass numbers. Going through, choice A, atomic number 6 and 7, those are different. 6 and 14 for choice B, those are different. Again, 6 and 14, those are also different. Yes, it could also be called magnesium 24 and magnesium 26, exactly. D, we have the same atomic number, and our mass numbers are different, so that one could be our answer. And then E, well, those atomic numbers are different between 8 and 16, giving us D as our answer. All right, let's go on to number 16. Which of the following shows the correct number of protons, neutrons, and electrons in a neutral cesium-134 atom? What do we know about a neutral atom? Well, a neutral atom means that our protons will equal our electrons. So right off the bat, let's see if there are any that differ between protons and electrons. Well, choice A, we have those the same. Choice B, those are the same. C, those are different, 55 and 79. So we can go ahead and cross that right off. The other two are the same. So we have cesium-134. So cesium is Cs. 134, that number is the mass number. Now, if we look at a periodic table, we find cesium, it's right here, and its atomic number is 55. So 55 goes on the bottom. Now, just like before, the bottom number, that is our atomic mass number. Not atomic mass, I'm getting confused. That bottom number is our atomic number, which gives us the number of protons. So our number of protons in this case is 55. So we can go ahead, cross off D and E, and that leaves us with A or B, both of which we have neutral, so 55 electrons, 55 protons in both. So we need to figure out the overall number of neutrons. Well, our atomic number, now I'm getting that confused. Our atomic mass is our protons plus our neutrons. So 134 for our atomic mass equals the protons, which we have at 55 plus neutrons. And then we can go ahead and solve that to get our number of neutrons equaling 79. And that is choice B. Yes, you do get a periodic table. All right. Some of you are going to get scared on the next one. Don't worry. We'll go through it. Number 17. That's going to be helpful. The complete photoelectron spectrum of an element is given above. Which of the following electron configurations is consistent with the spectrum? So, what is a photoelectron spectrum? This is essentially an electron configuration, just in graph form. And that's all it is. We've talked about electron configurations. You will always start over on the left. And the first peak is going to be your 1s peak. Then your 2s peak comes next. Then your 2p peak. Then your 3s. So it's just like going through your electron configurations, right? 1s, 2s, 2p, 3s, 3p. Just like it is. But what we want to also look at is the relative number of electrons. So in a 1s orbital, the maximum number of electrons we can have in an s orbital is 2. So we have 2 here. So the maximum number of electrons we can have in an s orbital is 2. And because we keep going through the photoelectron spectrum, then we can say that our s orbital is completely filled. So this s orbital is completely filled. This peak is 2 electrons. So each line here is 1 electron. And then this line is another electron. So 2 electrons, 3 electrons, all the way up. So if we were to look at this, we just start with our 1s, and it's completely filled with 2. Then 2s, again, we're at the 2 line for electrons, so that's 2. 2p, 1, 2, 3, 4, 5, 6, completely filled, 2p6. 3s, we have 1 electron, 2 electrons, so that's 3s2. And 3p, normally a p orbital when it's filled has 6, but we're not filled because we don't have 6 electrons. If we were to count, we have 1, 2, 3. We're on that third line, so that's 3p3. And so the complete photoelectron spectrum of this with the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3, which is choice B. Now I am going to answer some of these questions. How do we know what's S and what's P? So you always start, so I'm going to erase a lot of this. You will always start with an s orbital. Because if we look at the periodic table, when we read electron configurations, we always start at the top, which is in our S block. The first two columns, first two groups, make up the S block. So we'll always start with an S. And then as we go from left to right, we just want to make sure that we are sort of like reading a book. I know I don't have one with it, but let me see if I can quickly add to this one. I don't have one with me, but I'm going to quickly do it. So S with helium. Then we have... Oh, my power's like, my lights just flickered. Sorry. Then we have d orbital, p, and then f is on the bottom. So if we were to look at this, this might be a little bit easier to see. So we have our S block here. Then our P block comes next, because that's as we go left to right, we'll hit that one next. And then SP, our D block, comes next. And then the bottom one, which I don't have bracketed, will be our F block. So as we start up top, we always start with an S block, and we will go 1s, and we completely fill it. So each element we pass brings another electron, and then that will be 2 electrons. So as we go through, I almost wrote using the wrong one. As we go through, we have an S block, and then we have, as we go through our periodic table, S block left to right. We don't hit a P block, so we continue going down, and then we hit another S block. So we have another S. Then as we go through, we're now in the second row. We keep going across, and now we hit a P block. So we can use the configurations to find out what the element is. Absolutely. That is exactly what we do. So we hit a P, and then we go through and we do another S, and then this becomes a P. Now, how did I know which one was 1s, 2s, 3s? It's just the row on the periodic table. So we hit row 1 first, then we went down to row 2, then we went to row 3. And that's where those 2s and 3s came from. And then how did I know how many electrons? Well, an s orbital can have a maximum of 2 electrons. Yes, we just add helium to the s section. It's a funky one. So helium is technically, it can move over to the s orbital. An s orbital can have a maximum of 2 electrons, and since we're continuing to go over, we have more orbitals to fill. This one was completely filled with 2 electrons. So as we know that this is completely filled, we have 2 electrons. So if we look at the lines here, this peak tells us that this line is 2 electrons, which means this line must only be 1 electron. Then 3, 4, 5, and 6. And then we can fill in the rest from there. So we have 2s2, 2p6 because it hits line 6, 3s2 hits line 2, 3p3 because it hits that third line. All right, so that is that. So what you can do then is take this electron configuration and figure out, even though that's not what the question is asking, we can figure out what the element is. If we were to look, 1s2, 2s2, 2p6 covers all of these. Then we go down, 3s2, 3p3, we go, this is the third row. We're in the P section, 1, 2, 3. The element would be phosphorus. And so we can use electron configurations to help us figure out what element we are talking about. It is a lot of fun. So let's go on to another one similar to this. It's still a photoelectron effect. The complete photoelectron spectrum for an element is shown above. We're not told what element. Yes, the labs are posted on YouTube. Which of the following observations would provide evidence that the spectrum is consistent with the atomic model of the element? So again, we're given a complete photoelectron spectrum. So our first line that we see, our first peak, that's going to be 1s. Then our next one, if we were to look at that periodic table again, we would hit 2s for our next peak. Now this is a complete photoelectron spectrum. So because we hit the 1s and then we go to 2s, we completely filled this s orbital. So we have 2 electrons in there. This line is 2. So each one of these lines is 1 electron. So we have 1s2, 2s1, because that peak only went up to that 1. So 1s2, 2s1, meaning it's lithium, right? So if we go 1s2 completely fills this. 2s2, we go 2s1, sorry, 2s block with 1, we have lithium. So this technically is the photoelectron thing for lithium. But let's see what the answers are sort of looking at. A neutral atom of the element contains exactly 2 electrons. Well, a neutral atom, so if we have just like this, a neutral atom, that would be 1, 2, 3 electrons. So this one would actually be 3 electrons, not 2. The element does not react with other elements to form compounds. That is notable for noble gases. Noble gases have a complete octet. They're full. They don't want any more electrons, so they can't really react. There are some exceptions, but they can't react. And since we're talking about lithium, something that is has a 2s1, that's not a noble gas. Lithium heavily reacts. That is 100% true. In its compounds, the element tends to form ions with a charge of +1. Well, if we look at our sort of where lithium is on the periodic table, lithium is in group 1 on the periodic table. And because it's a metal, it's to the left of this staircase. It forms positive ions, cations. And it's in the first group, so it only likes to lose its only electron, that 2s1 electron, making it a +1 charge. So that one could be correct. Let's just double check and make sure that the other one is not. In its compounds, the element tends to form ions with a charge of +3. We just said that that one forms a charge of +1, so C is the correct answer. How's everyone doing? Oh, I love going through these lives. We have 26 questions, multiple choice questions, and then we'll go through maybe like 2 free response style questions. So we have a couple more multiple choice questions left, and we are going to get into some trends on the periodic table now. These are AP Chem exam. This isn't an AP Chem exam, but the questions are from AP Chem material. Yes, 100%. So now let's talk about some trends on the periodic table. Which of the following elements has the highest electronegativity? So what is electronegativity? Well, electronegativity is the want for electrons. It really wants to have a negative charge. So something that wants to have a negative charge is going to be a nonmetal, because those form negative charges. It wants to have it wants to gain electrons, essentially. And so the trend on the periodic table is as you go from the bottom left to the top right of the periodic table, minus the noble gases because they are very unreactive. So bottom left to top right, those you will increase in electronegativity. So as you go from bottom left to top right, this is the trend for electronegativity. You will increase as you go that way. So if we look here, we have cesium, silver, and lead. So we have cesium down here. That's very not electronegative. You have cesium, silver, and lead. So silver's here. and then lead is down here. So these could be our answer. Then we have bromine and selenium. So selenium is up here. So right away, selenium already takes the cake over silver and lead because it's further up to the right on the periodic table. And then we have bromine as our final, which is all the way over. So bromine is more electronegative than selenium. So our most electronegative, or the thing that has the highest electronegativity, is choice D, bromine. Which of the following elements has the largest atomic radius? Well, atomic radius, I'm moving my leg. There we go. Atomic radius has the opposite trend. As you go from the top right to the bottom left, you are increasing. So I'll put this increase electronegativity. This is going to be increase in atomic radius. So as you go from the top right to the bottom left of the periodic table, our trend is that we are increasing our atomic radius. And so we just looked at the position of each one of these, and we saw that cesium was all the way down here compared to the others, which were over here. Absolutely. So we have cesium, which is over here. And then we have, I don't remember what they were, silver and lead, selenium, and bromine. So all of those other four over here, atomic radius is over here. So our choice correct answer is A for cesium. But why is that? Well, remember, as we go from the top of a group down, we're adding another shell. And as we add another shell, we increase the radius. We add another shell of electrons. So H only has one shell of electrons. Potassium has 4 shells. So we're getting bigger and bigger and bigger and bigger. And then the reason why it's this way is the effective nuclear charge is smaller. So it has to do with Z effective. So the further you go down and to the left, the bigger you get. And the last one, which of the following elements, well, the last one for this trend question, which of the following elements has the lowest first ionization energy? Now, the first ionization energy trend, I'll show you and then we'll talk about what it means. It increases as you go from bottom left to top right. So increase first ionization energy. And that is, if we talk about something like ionization energy, you are essentially, ionization energy is the energy you need to put into something to get rid of an electron or to put an electron in. So it's the energy needed to either become a +1 or a -1 charge. So the first ionization energy increases as you go from the bottom left to the top right. And we're looking here for the lowest first ionization energy. They are related. They're not exactly the same, but they are related. Yes. So here, we're looking for lowest, which means we're looking for something down here. These are still the same 5 elements that we were talking about. And so our lowest to the bottom left was cesium. So that one is going to be cesium with the lowest. You're not cooked for the AP exam. I believe in you. Cesium's working overtime. I know, we got to give cesium a break. Let's give cesium a break and we'll talk about calcium and potassium. What app did he use for the drawing and the image of the exercise? I don't know what exercise that might be, but I use Notability for all of these. I do take screenshots of the questions from AP materials, but so like I don't produce these images, but the images that I draw on and stuff is notability. Based on periodic trends, so number 22, based on periodic trends in the data in the table opposite, which of the following are the most probable values of the atomic radius and first ionization energy for potassium? So again, this is using trends in the periodic table. We are given values for calcium. We have an atomic radius and a first ionization energy, and we need to figure out the estimated values of potassium's atomic radius and first ionization energy. So let's figure out where those two are. We have calcium and potassium. Calcium, let me move my hand. Calcium is right here, and potassium is right here. So we have, I'm just going to draw this down here. So potassium and calcium. They're in the same row, and they potassium is further over. So it goes potassium, then calcium. Now, we just did the atomic radius trend, where we said as we go from top right to bottom left, we are increasing our atomic radius. So as we go further left, our atomic radius increases. So the atomic radius for potassium, we want to be higher than calcium because it's further to the left. It's following that trend on the periodic table. And for our first ionization energy, we said that we're increasing as we go from left to right. So because potassium comes before calcium, it's going to have a smaller first ionization energy. And so the correct answer here, looking at the values that are given as our answers, we want a larger atomic radius, so C and D are out. And then we want a first ionization energy to be smaller than 590, which is choice B. Amazing. Nice job, everyone. We have 4 more multiple choice. 4 more multiple choice in this section. We're getting there. I'm going to rest my voice for just a sec. Okay. Number 23. The ionization energies for the element X are listed in the table below. And we're given 1, 2, 3, 4, 5 ionization energies. On the basis of the data, element X is most likely to be what? So let's talk about what these values mean. Right? Ionization energies is the energy needed to ionize something. That sounds counterintuitive, but if we had a solution or an element F, fluorine, and we wanted to get it to its F minus, we wanted to make it an ion, it takes energy to put an electron on that fluorine. And the amount of energy it takes to put on that fluorine is an ionization energy. Now, that would be the first ionization energy because it's just putting one electron on there to get a -1 charge. Let's say we wanted to get an F2 minus charge. Well, fluorine likes to be a -1 charge, right? It likes to, if we look at the periodic table, it likes to gain an electron. And if it gains 1 electron, it acts like a noble gas. And because it's acting like a noble gas, it's happy, it does not want to move. So if we want to add another electron onto here, the amount of energy that we're going to need is going to be significant. It's going to be so much energy that we need to put in. So this would be our second ionization energy, but we would see a huge jump between the first and the second. So we would see maybe like 500 versus like 7,000. We would see a huge jump in energy needed because it doesn't want to do that. So looking at the data here, we see that we have 580 for our first. Then we jump up a little bit. It's still comparable to 580. Still comparable going from second to third. So we remove 1 electron, either remove or add 1 electron, remove or add another electron. Same thing here. But what happened as we went from the third to the fourth? We jumped in our ionization energy. And so this is where our element X is happy. It likes to only gain or lose 3 ions. So looking at this, our element X will either gain or lose 3 electrons. It will only ionize 3 times. And what we're going to do is find an element that likes to gain or lose 3 electrons. So sodium was one of these things. Look for which one doesn't like to add or lose 4 electrons. Exactly. So sodium likes to gain or lose 1 because it's in group 1. Then I think it was magnesium, which is 2, so it's going to gain or lose 2. Aluminum, it'll gain or lose 3. So aluminum here is our answer because we are going to be losing or gaining, which is popularity plus 3 as its ion. Exactly. There, yes. So aluminum would be our answer here. You're always going to want to look for that jump wherever it significantly increases. Yes, these PDFs are available on my link tree. It's under helpful information, and then it'll take you to a Google Drive where you can actually look at these. I post the PDF of the problems the day of or day before, and then the answer key afterwards. All right. Which of the following, number 24, which of the following lists magnesium, phosphorus, and chlorine in order of increasing atomic radius? So using that trend in the periodic table, we know that atomic radius will increase as we go from the top right to the bottom left. So if we look, we have chlorine, or magnesium, phosphorus, and chlorine. We have chlorine here, phosphorus, and magnesium. So magnesium is going to be the largest because it's all the way over, right? We're increasing as we go from the top right to the bottom left. So we see chlorine first. So that's going to have the smallest radius, then phosphorus, then magnesium. So we go chlorine is the smallest, phosphorus next because it appears, it appears next, and then we go magnesium. So this is choice A. Well, welcome, law graduate. I wish I knew a little bit about the law. And then sometimes I'm like, no, I don't. There's a lot of reading. I'll stick with my sodium and chlorine. Number 25, let's finish these 2 multiple choice, and then we'll go on to a couple free response. So if sodium reacts with chlorine to form NaCl, which of the following elements react with sodium to form an ionic compound in a 1-to-1 ratio, and why? So if we look, we have sodium chloride that's being formed. So sodium reacts with a chlorine in a 1-to-1 ratio. Now, we're looking for something that is dealing with reactivity. Now, with reactivity, we want something to be in the similar group because a group on the periodic table or a column on the periodic table has similar reactivity. And that's because they have the same number of valence electrons or electrons in the outermost shell. So it can do the same sort of chemistry. So if we're looking for an element that reacts with sodium, we want an element in the same group as chlorine. So if we look at chlorine, we want one of these elements to be in our answer. And the answer we see here, not potassium, magnesium, or argon, but we see bromine. And bromine, because it has the same number of valence electrons, so it can do the same reactivity. Remember, everything in the same group will have similar reactivities. And the last one here, atoms of element X, we like element X for some reason. What is a 1-to-1 ratio? I'll go back to that. So 1-to-1 ratio just means that we have 1 sodium and 1 chlorine forming a bond. We could have things like magnesium, I'm not going to use magnesium because it's the next one, but like Na2S, for instance, that would be a 2-to-1 ratio because we have 2 sodiums for every 1 sulfur, something like that. So when we say a 1-to-1 ratio, it's just the number of sodiums to the number of chlorines that we have. All right, the last multiple choice. Atoms of an element X have the electronic configuration or electron configuration shown right here. The compound most likely formed with the magnesium is what? Well, let's take a look at this electron configuration. I'm going to zoom in slightly. We have 1s2, 2s2, 2p6, 3s2, and 3p3. So we have 1s2 that goes here. Then we go to 2s2, completely filled. We go all the way over. 2p6 was completely filled. Then we go down to 3s2, which was filled. And then we go all the way over to 3p3. So 3p3, we're in the third row. We're in the p block, and we go 1, 2, 3. So we're talking about phosphorus here. Now, something with that configuration would have a -3 charge because everything in this column, in this group, has a -3. It likes to gain 3 electrons to act like a noble gas. So because it's in this column, it's going to have a charge of -3. So our X will have a charge of -3. Now magnesium, because magnesium would be, it's in the second group, that has a charge of +2. It's a metal. It likes to lose 2 electrons to get to the noble gas to be happy. So we have magnesium 2+ and X 3-. So we can do the crisscross applesauce, where we take the 2 from our magnesium and crisscross it down to the subscript X, and the 3 comes to the subscript Mg, and we get Mg3x2. Another way to think about it is how many magnesiums do I need and how many X's do I need so the charges are equal but opposite sign. Well, the least common denominator, least common multiple, LCM, is it's going to be 6 here, which is 3 magnesiums and 2 X's. So the correct answer here is choice E. I saw a couple of those back in the chat. All right. So those are the multiple choice questions that I selected. I'm going to skip around on the free response. We're going to do... We're going to do all 4 of them, but I'm going to start with... I'm going to work backwards. So I'm going to go over to this one first, and then we'll kind of just work our way backward. So number 4 on the free response. The complete photoelectron spectrum of an element in its ground state is represented below. So we have this photoelectron spectrum. Now remember, we always start with a photoelectron spectrum. We always start with 1s, and then we continue going elsewhere. So 1s here, then we have a 2s and 2p, then we have 3s and 3p. This is all from the orbitals, and then we have 4s there. So those are just the peaks, the different orbitals. Based on the spectrum, write the ground state electron configuration of the element. So we're looking for an electron configuration of the element. We just sort of talked about how each one of these is 1s, 2s, 2p. So the last thing we have to figure out is how are we going to figure out the number of electrons in that orbital? Because we're told that it's a complete photoelectron spectrum, and we're talking about ground state, meaning no electrons are excited out, we're going to completely fill our first orbital, which is 1s2. So this line right here tells us that that is 2 electrons, meaning half of it is 1 electron, and then we can kind of keep going. This is 4, and this is 6 electrons. because that's the relative number of electrons. So 2 in an s orbital, so on and so forth. So if we wanted to write the ground state electron configuration of this element, we'll just go from left to right. 1s2 completely filled, 2s2, it hits that line 2. We're now on our 2p line, and it goes all the way up to 6. Then we hit our 3s, and it goes and hits that second line, or the first line, meaning 2 electrons. And then we're at our 3p peak, and it goes all the way up to 6. And then we're at our 4s line, and that is filled at 2. So this is our ground state electron configuration of the element, and we can use this to solve and identify the element. Now, what you do is you just sort of work your way all the way across. I also like to just look at the last little bit, because 4s2 means we're in the 4th row, so 1, 2, 3, 4. We're in the s block, so we're in the right spot. And then we completely fill that orbital, so we go over 2, 1, 2. This element is calcium. Then it asks us to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. So we're talking about the valence shell. Now, the valence shell is the outermost layer of electrons. Now, the outermost layer of electrons, we always will be able to figure that out based on the number. So our numbers, 1, 2, 3, and 4, those correspond, I'm going to write down here just for a moment, to the layers of electrons. So we have 1, 2, 3, 4. Our valence electrons are the outermost layer. So that number just tells us the shell of electrons. Now, we're going to use the energy equation. Energy equals hc over lambda, where h is Planck's constant, c is the speed of light, lambda is our wavelength, and energy, E is our energy. Now we're talking about the energy associated with our valence electrons, which is this binding energy here, given up in the problem, or in the graph. Since we're looking for wavelength, I'm just going to reorganize, work this equation to give us lambda, to solve for lambda. So I'll multiply both sides by lambda, our wavelength, and I'll divide by energy. So just rearranging, we get lambda equaling hc over our energy. So now we can plug in h and c are constants, those won't change, and energy we're given. So now it's just a plug and chug. We have lambda equals our Planck's constant, that's 6.626 times 10 to the negative 34 joules times seconds. Speed of light is 2.998 times 10 to the 8th meters per second. And then our energy from above is 0.980 times 10 to the negative 18 joules. When we solve this out, we get a wavelength equaling 2.03 times 10 to the minus 7 meters. And remember, we're looking for it in meters. Sometimes it'll ask you for nanometers, or I've seen micrometers, things like that. But here, we just want it in meters. And just to verify that the units cancel, joules will cancel out, seconds cancel out, and we're left just with meters. And that's how you would do that one. So we're working backwards on the free response. The 2.998, that comes from the speed of light. So this is the speed of light. Speed of light, that is given. And this is Planck's constant. Planck's constant, that is also given. So those two values are given. And then the 0.980, that came from our binding energy up top. All right, let's go backwards to number 3. Answer the following questions related to the analysis of calcium bromide. A student has a 10-gram sample of calcium bromide, CaBr2. Show the setup of the calculation to determine the number of moles of calcium bromide in the sample. Include units in the setup you do not need to calculate. So here, we're just looking for the setup. We're not asked to actually solve for this problem, like the actual answer. So we want to go from grams into moles. And how do we go from grams to moles? If CaBr2 was a person, it would be a cabaret dancer. That's awesome. I love those types of things. So when we go from grams to moles, we use the molar mass. I'm going to shorthand that to MM for molar mass. Nice job. So here, let's set this up. We have 10.0 grams of CaBr2. Now it wants us to use units, so I'm going to make sure to include those units. Ooh, that's a shaky line. So we have our units there. Now we want to go from grams into moles. So I'm going to cancel out grams of CaBr2 and go into moles of CaBr2. We are using the molar mass, so we're just canceling out units using dimensional analysis. And then if we were to look up on the periodic table, we would see that calcium and 2 bromines, the molar mass would equal 88 grams for every 1 mole. Now, because we're not asked to solve this, we're just asked to set it up. This is all you would have to do. And for part B, what number, in addition to the answer to part A, is needed to determine the number of atoms of calcium in the sample? So now we're looking to go from moles using this, because this is part A, we figured out moles. We want to go from moles to atoms. How do we go from moles to atoms? This is our favorite one. Avogadro. We eat them? Yes, you can eat avocados. Absolutely. But we're going to use avocado's number or Avogadro's number. We're going to go, so the number that we need is Avogadro's number. Avogadro's number, which is 6.02 times 10 to the 23rd. And then the units here are something per mole, or mole to the minus 1. 6.022 times 10 to the 23rd, absolutely. And then part C, a different student is given a 10-gram sample labeled calcium bromide that may contain an inert non-reacting impurity. Identify a quantity from the results of laboratory analysis that the student could use to determine whether the sample was pure. So this one is this one's worded very strangely. We want to just look for or identify some sort of technique or value that we can find in the lab to tell whether or not this is a pure sample. And that's all this question is asking for, is what technique, what value can we use that we can solve for in lab to figure out if it's a pure sample or not. And so when we're talking about this, we can use, so the student can use melting point analysis. Because if something is a pure compound and there's no impurities, its melting point will be like spot on to the actual melting point. So let's say the melting point for this was 82 degrees. It'll be somewhere right in there. But if there was an impurity, so it was impure melting point, that would lower the melting point and it would actually be a range. So now instead of 82, we might have like 71 to 78 degrees Celsius. So it lowered the melting point, meaning that there's something contaminated in it. So using a melting point analysis is good in the lab so we can see if there are any impurities left in the sample. All right. How is everyone doing? We have two more problems. We have this one here, and then we have a long free response problem, which is 2 pages. So, and then that'll be the full packet. And I can't believe we've been doing this for 2.5 hours so far. This is going to be a long video on YouTube. Melting point, yes. So melting point, if we go back here, melting point of a pure substance will be very exact. So melting point of water, for instance, is 0 degrees Celsius. So if you have like 0 degrees Celsius for water, that is the melting point. It's going from a solid to a liquid. But the melting point, that's actually not a good example. But in any case, if we were to have some impurities in this water, the melting point would actually be lower, and it could be like -2 degrees Celsius or something. So it's not the exact melting point. So a melting point, what they do is they take a little bit of your sample and they just heat it up and heat it up, heat it up until they see it melt. And there's actual instrumentations that can get like very specific on your melting point. But if you heat it up and you notice that the melting point when it starts to melt is different than the actual melting point, then you have some impurities, something not good in your sample. All right, let's go on to number 2 on the free response. Based on the photoelectron spectrum, identify the unknown element. Oh, let me read this up here. The photoelectron spectrum of an unknown element is shown below. That's, yes. So all you would have to say is they can use melting point, unless it asks you to justify. That one didn't, so we didn't justify. Based on the photoelectron spectrum, identify the unknown element and write its electron configuration. So again, with a photoelectron spectrum, we always start with our 1s on the left, the first peak, and then we just use our orbital notation, 2s, 2p, 3s, 3p. Each peak goes in the next orbital. So here, because we have our photoelectron spectrum, our s orbital is completely filled. So this line tells us it's 2 electrons. So each one of these lines, 1, 2, 3, 4, 5, 6, is a number of electron that we have. So our electron configuration would be, we start with 1s, it hits line 2. Then we move over, we hit our peak for 2s, and that also hits the line 2. We move over to our 2p peak, and that goes all the way up to 6. We see our 3s peak goes to 2, and our 3p peak, that's funny, goes to 3. So this would be our electron configuration. I'm going to rewrite that 3 just so it's a little bit neater. And then we look at the periodic table. We go 1s2, 2s2. We go all the way over. 2p6 was completely filled, so we go all the way over. 3s2, we're in the third row, the s block, and we go over 2. We go here, this is 3p, we go 1, 2, 3 for 3p3, giving us phosphorus. So our answer here is phosphorus for the element. If the peak energy was in reverse, would the electron configuration be reversed? Yes. So if it started at point 1 here, and went up to 1,000, then it would be reversed. That is correct. Most of the time, though, at least it's not cesium. That is true. It's been a while since we had cesium. Most of the time, though, you will it will give you your binding energy as starting over here. So you will do 1s first. My cat is getting a little antsy. I don't know if you can see. There she is. There we go. All right. B, consider the element in the periodic table that is directly to the right of the element identified in part A. Would the peak, so there's a typo here. This should say, would the 1s peak? So I'm just going to do would the 1s peak of this element appear to the left of, the right of, or in the same position as the 1s peak in the element in part A. So let's talk about what this is asking. So we have phosphorus on the periodic table. So we have phosphorus. It's asking us to figure out the element directly to the right. Well, that's sulfur on the periodic table. But would this element, would its 1s peak, so we're talking about this peak here, would this 1s peak be in the same position? Would it be to the right or to the left? And this all comes down to number of protons, really. So since the element to the right here has more protons, it's going to result in a higher nuclear charge, or a Z effective. Ooh, I hit the wrong button. So when we increase our Z effective, or our nuclear charge, we are increasing our binding energy. So if we were to write this out, this is how I would put it. I would say the 1s peak would be to the left, because we're increasing energy, so it's going to be to the left. Would be to the left of the peak in part A. That's what it is. So the 1s peak would be to the left of the peak in part A, because the element to the right of phosphorus has more protons, resulting in a higher nuclear charge and an increase in binding energy. And that's how I would explain this. Because we're increasing our number of protons, we have a higher Z effective, or a higher nuclear charge, resulting in a higher binding energy. And our binding energy increases as we go to the left, so the peak would be to the left. So yes, our number of protons increases our Z effective, because Z effective increases as you go from the left to the right. You're increasing the amount of protons, you're increasing your nuclear charge. Perfect. I know that one was a tough one. We got one more free response. It's a longer one, but it is a very, very common type of question. It's gravimetric analysis. So we'll go through this question and then we'll be done for the night. So if you're just joining, we have gone through 26 multiple choice questions, a little bit of review, and this is the fourth of 4 free response questions. All of these problems are available on my link tree if you want additional practice, and they will be, this whole live recording will be up on YouTube. I'm posting those there, as well as a lot of the content that I post on TikTok. That way you can find it easier, because I find it a little hard to find things on my TikTok even when I post it. So even though I'm the one that knows where it is, I find it difficult to find. So let's go through the last free response question. Answer the following questions relating to gravimetric analysis. In the first of two experiments, a student is assigned the task of determining the number of moles of water in 1 mole of magnesium chloride .NH2O. Now this .NH2O, that is a hydrate. The water is sort of trapped inside that magnesium chloride. It's not directly bound to it, it's just sort of there, it's chilling out. The student collects the data shown in the following table. So we have the mass of empty container, initial mass of sample and container, after first heating, second heating, third heating. Explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. I see the answer already popping up. So if we look here, our mass between the first and the second, heating afterwards didn't really change that much. It went down a little bit, so 0.982 to 0.976. So we decided to heat it again, and then we see that it didn't really change. So here, we're looking for, whenever we're doing gravimetric analysis, we want to make sure that the weights, the masses, remain unchanged. That means no more water is being evaporated. So here, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times. Well, it's because no additional mass was lost during the third heating. This indicates, or indicating, water, H2O, indicating all the water has been removed. So as long as you say something along those lines, then you will get full points. That because the third heating, the mass didn't really change, you're good. So part B, use the data above from the table to calculate the total number of moles of water lost. So this is where we're going to look at the table and really figure out how we can determine anything about the water. So we have here the mass of the sample and container, and the mass after, so the sample and container after we heated. The difference between this mass and this mass is going to give us the mass of the water. Now the mass of the water will give us a value in grams, but we're looking for number of moles. So we're gonna do a subtraction, get grams, and then we'll go from grams into moles using the molar mass. Okay. So here, let's go ahead. I'm going to start doing this, but if you want to do it off to the side, we have 23.977 grams, and we'll subtract from that 22. Nope, I'm on the wrong problem. Sorry. Oopsie. We're going to start with the 25. That's what I want to start with. The 25.825 grams. That's our mass of the unhydrated, or non-hydrated. Mass of the hydrated, that's the one. And we'll subtract from the mass of our dehydrated, so that's the 23.977 grams, giving us a total mass of water in our sample of 1.848 grams. But that's not what the question is asking. Remember, we're looking for a number of moles. So we have to go from grams into moles. And how do we go from grams to moles? Well, we use the molar mass. So we have 1.848 grams of water, and we're going to use the molar mass of water, 1 mole of H2O. We add up 2 hydrogens and 1 oxygen, giving us 18.02 grams of water. And that gives us a total number of moles of 0.1026. moles of water. And that is our answer for part A, or part 1. All right. Number 2, determine the formula of the hydrated compound. So we're going to be looking for this part. Essentially, we're looking for N. What is N? You can round to sig figs here, and these types of problems, you don't necessarily have to, but you definitely can. So here, determine the formula of the hydrated compound. Well, what we're going to do first, and I'll explain this, and I'll explain what we're going to do. Since we want to solve for N, we're really looking for the molar ratio between magnesium chloride and water. Now, how do we find a ratio? Well, we need to compare the amount of moles. So the first thing we're going to do is solve for grams of magnesium chloride and convert that into moles of magnesium chloride. And then once we figure out the moles of magnesium chloride, we'll have the moles of that, and then we also just found the moles of the water. So now what we'll do is after that, we will compare the moles of MgCl2 and moles of water, and that'll give us our N value. So let's go ahead and solve that. To figure out our mass of magnesium chloride, we're going to take the mass of the dehydrated sample, so the one without the water, and the mass of the empty container, and we'll do a mass by difference. So then we can say, well, the mass of our dehydrated sample, that's the 23.977 grams, and we'll subtract from that the 22.347 grams. And that, I'm running out of room here, but that will give us a value of 1.630 grams of magnesium chloride. In order to go from grams to moles, we use the molar mass of magnesium chloride. So we go from 1 mole of MgCl2. Figure out that molar mass of magnesium chloride is 95.20 grams of MgCl2, giving us a value that is equal to 0.01712. So a lot of values here. Moles of magnesium chloride. So that was step 1. We solved for grams of magnesium chloride, and then we changed it and converted it into moles. But now we want to compare our moles of magnesium chloride and moles of water. So off to the side, I'm going to do this over here. Just like we did with empirical formula, we're going to take the smallest of the two and divide them. So the smallest of the two is magnesium chloride, so we'll take the 0.1026 moles of water, divide that by the smallest, which is 0.01712 moles of MgCl2, and that will give us a value equaling 6. And what this is saying is for every 6 moles of water, we have 1 mole of MgCl2. And so when we write out our final formula, we have 1 mole of MgCl2 has 6 moles of water. And that is the final answer for part 2. So let's keep going. We have a couple more left. Just a couple more. A different student heats the hydrates in an uncovered crucible and some of the solid spatters out of the crucible. The spattering will have what effect on the calculated mass of water? So what we're really saying is, as we're heating it up, some of the sample is being removed. It's sort of spattering out. Now, because it's spattering out, our final weight is going to be lower than what we calculated. Now, if it's lower, then the mass of water we calculate is going to be higher because we do final minus initial, or we sort of do, final minus initial. So our final will be much, much higher. So here, something to justify, I'm going to use a different color just so we don't get confused here. I'll do this. The calculated mass of water lost would be too large, since the mass of solid lost due to, I'm running out of room, due to spattering would count as mass of water evaporated. Spattering counts as water evaporated. Counts as H2O evaporated. There we go. Beautiful. My name is actually Bradley. I see the chat. Don't worry. My name is Bradley. My parents named me Bradley Taylor. So, we're going to continue here. This will be posted. Don't worry. I can go back. I can catch my breath for a moment. My brother's name is Steven, just with a V, not a PH. I do have golden retriever energy. There's nothing wrong with that. Oh my goodness. So what I love so much about people, and this is not related to anyone here, but what people think is they give comments on my videos that think they'll get to me. And no matter the hate comment, it doesn't get to me. I will always respond with like positivity or like sarcasm or something. Like no one gets to me. We did multiple choice earlier for the first 2 hours. This is our final free response. All of these are available on my link tree, and we do what was I gonna say? I post these on YouTube. I know nothing here. But the people who are always like, oh, you know, I can't even think of one, but some of them, like trolls, think they're getting to me, and I'm like, absolutely not. So let's go through the final 2 problems, technically 3, but final 2. In the second experiment, a student is given 2.94 grams of a mixture containing anhydrous, meaning no water, magnesium chloride, and potassium nitrate, so MgCl2 and KNO3. To determine the percentage by mass of magnesium chloride in the mixture, the student uses excess silver nitrate to precipitate the chloride ion. So starting with the 2.94 gram sample in the mixture dissolved in water, briefly describe the steps necessary to quantitatively determine the mass of AgCl. So essentially what we are doing in this problem, we want to remove the silver. We want to get rid of that silver chloride, and we want to figure out how much, because quantitatively, how much we are going to have. So the steps to do this, after we add the excess silver nitrate, so we add that excess silver nitrate like it says up here, it's going to precipitate the chloride ion. So in our solution, we'll have some of our solution, and then we'll have these sort of solid precipitates, a solid forming. Now, how do we get rid of that solid? Well, the first thing we're going to do is separate that solid AgCl that we're forming by filtration. That'll get rid of all of that solid. Well, it'll separate all of the solid from the liquid. So we use some sort of filter paper or something like that, and it'll be filtered out, so we'll just have the solid. But we want to quantitatively determine the mass. So what we want to do next is wash and dry that solid, because we don't want any sort of impurities. We don't want anything to still be there. So we just want our pure silver chloride. And then the third step, once we dry it all out, is just determine our mass by difference. Mass of AgCl by difference. We'll take the mass of, we'll just take the mass, sorry, not the mass by difference. So we'll just take the mass of whatever it is. And those are the steps. We added our AgNO3, we precipitated it out, and then we separated it by filtration. We washed and dried it, and then we weighed it. AgCl, low-key, the Mariah Carey, if you really think about it. I don't know what that means, but sure. All right, so part E. The student determines the mass of AgCl precipitate to be 5.48 grams. On the basis of this information, calculate each of the following. The number of moles of MgCl2 in the original sample. So what we need to do is figure out a couple things. This is going to look a little strange. So we are given a mass or grams of silver chloride. So we have grams of silver chloride. But we want to figure out MgCl2. Now the thing that that's useful between these two is the amount of chlorine, right? We have a common ion in there. And so we are going to solve for something with chlorine and then use that. But what do we have to do? Well, we have to solve for moles first. All when in doubt, just solve for moles. So first thing we're going to do is take our 5.48 grams of silver chloride, and we'll convert that into moles. So 1 mole of silver chloride is to, if we look on the periodic table, we get 143.32 grams. And that's going to give us a value of 0.0382 moles. So now that we're in moles of silver chloride, we can then use that to solve for some other things. So let's go ahead and use that. We have 0.0382 moles of silver chloride, but we want to be in something that can connect both the silver chloride and the magnesium chloride, and that is chlorine. We no longer want to be in moles of AgCl. We want to be in moles of chlorine. So looking at this, if we had 1 mole of AgCl, how many chlorines do we have? Well, we have 1 chlorine, right? If I gave you 1 AgCl, we only have 1 chlorine in that compound. But we don't want to just stop there, because that'll just give us something in moles of chlorine. We want something in moles of MgCl2. So we're going to go one step further, and we're going to get rid of moles of chlorine on the bottom, going into moles of MgCl2 on the top. If we had 1 mole of MgCl2, how many chlorines do we have? Well, we have 2 chlorines. We see 2 as a subscript there. And when we do that math out, we get a value equaling 0.0191 moles of MgCl2. And for the final one, the percent by mass of MgCl2 in the original mixture. So percent by mass means we have to be in grams. We'll do grams of part over grams of whole. So we're going to take our moles that we just found of our MgCl2, and we're going to convert that into grams using the molar mass. That's 95.20 grams of MgCl2 for every 1 mole of MgCl2. That gets us a mass of 1.82 grams of MgCl2, but we want mass percent. So mass percent equals part over whole times 100. I'll do mass here, mass percent. So mass percent here, our part is 1.82 over our whole at the very beginning of the solution was 2.94 grams times 100% gives us a mass percent of 61.9% MgCl2. And that is our final answer. My goodness, that was a lot of work. So let me flip this around. Flip camera. Nope, flip back. There we go. So that was a lot of work, but I hope it was helpful to you. If you want to try these practice problems on your own, they are available in my link tree. Hi everyone. This is me. I guess I have a filter on because I don't look this great. But if you want to try these practice problems, they are available on my link tree. As soon as I'm able to, this video of this live recording will go on YouTube along with a bunch of the problems and stuff that I go over on my TikTok. If you have any specific questions, please feel free to send them my way. My DMs are always open, but I can't guarantee that I will get to everyone. I would love to do a Q&A, but I have been on live for 3 hours now, and I have some other things that I need to get done. But our next live is Wednesday at 7 p.m. Eastern, I believe, and we'll go over Unit 2, which is compound structure, bonding. I don't remember what Unit 2 is, but it's just like this one, just different. We'll go over molecular theory and stuff. In any case, have a wonderful night, everyone. And remember, keep on being amazing. You got this. I know you do. All right. Have a great weekend. Enjoy the eclipse if you are around that eclipse area. But have a wonderful night, everyone.